Hello everyone, my name is Jingyi Xu, and I'm glad to introduce to you algebraic machine reasoning. In our previous video, we have briefly explained the intuition of how algebraic machine reasoning is used to solve Raven's progressive matrices. In this video, we are going to further describe the process of solving RPMs in detail. Let's start by reviewing the composition of RPMs. A typical RPM instance is composed of a question matrix and an answer set. The question matrix is a 3x3 grid of panels that satisfy certain hidden rules, while the first 8 panels are filled with geometric entities, and the 9th panel is missing. This RPM instance on the right will be used as our running example to show the entire algebraic reasoning process. In our paper, the algebraic machine reasoning algorithm is designed to solve two tasks. The first answer selection task is to infer the correct answer for the missing panel from the 8 panels in the given answer set. The second answer generation task, which is much more difficult, aims to generate answers without needing a given answer set. Our algebraic machine reasoning framework can be roughly divided into two stages: algebraic representation and algebraic machine reasoning. In order to encode the RPM images algebraically in the first stage, we first need to train object detection models on a small subset of RPM images to detect entities and their attribute values. Each panel can then be represented as a concept according to the detected entities and attribute values. In the second stage, there are 3 steps to extract row-wise patterns from RPM images, and then either select or generate answers, which I will describe later. Please recall that we introduced attribute concept to categorize the attribute values. Intuitively, an attribute concept is a concept constructed by combining primitive concepts that represent task-specific attribute values. For more details, please refer to our paper and the previous video. Let's consider those attribute values that are involved in our running example. Note that the variable labels such as xcircle or xflag are used for easy understanding. We shall use the corresponding indices instead for algebraic computations. Then, for each attribute from number, position, type, color, and size, the attribute concept is defined as the concept generated by all the possible values for this attribute. For pattern extraction in this paper, we shall use the inductive bounds that a concept representing a pattern is deemed meaningful if it is in some attribute concept. Let's move on to the first algebraic representation stage. According to the perception results obtained from object detection models, each panel can be encoded as a concept. For example, the first panel in the question matrix can be encoded as a concept J11 in the polynomial ring R. Since the object detection models detect 2 entities in this panel, there would be 2 generators in J11, where each generator is a monomial of degree 5 formed by multiplying 5 variables together, where these variables represent attribute values of the corresponding entities. Similarly, we can encode the remaining 7 panels of the question matrix and the 8 answer options. We define the concept matrix as a 3x3 matrix of concepts indexed from 1, 1 to 3, 2. In the second stage, there are 3 steps for algebraic reasoning. The first 2 steps aim to extract row-wise patterns from the first 2 rows of the question matrix, and the process are exactly the same for both answer generation and answer selection tasks. The only difference lies in the way to make use of these extracted patterns. Now let's move to step 1, splitting panels based on entity position. The purpose of this step is to allow reasoning about patterns that involve only a portion of the panels. For example, we can find that the shape of outside entities is invariant across all 3 panels in row 1. However, the same pattern doesn't exist for the inside entities. Hence, we can extract more patterns when we focus on only a portion of the panels. In this paper, we only consider those common position values among all 8 panels in question matrix, which can be computed with the following equation. Then, for each common position P, we can generate two new concept matrices, J bar P and J hat P. Intuitively, J bar P represents the panels that only contain entities on this position P, and J hat P represents the panels that omit the entities on this position P. Consequently, we will generate a list of concept matrices at the end. For our running example, we can first compute the set of common positions x out and x in. Note that we can consider a list of only 3 concept matrices, as focusing on a position is equivalent to omitting the other position when there are exactly 2 entities in each panel. From the first stage, we have already encoded the question matrix as a concept matrix J. Note that the first generator in all 8 concepts are divisible by x3. Hence, we can generate the concept matrix J bar x out, where each concept is generated by the first generator in the corresponding original concept. Similarly, we can also generate the concept matrix J bar x in. In step 2, we shall extract row-wise patterns from the first 2 rows. Recall that we propose 4 invariance modules to extract different types of patterns from any sequence of concepts J1 to Jk, which can be computed using the following equations. For each concept matrix in the list, we shall apply the 4 invariance modules to row 1 and row 2, and find the patterns that are common to both 2 rows. Below are the sets of common patterns extracted from each concept matrix. Patterns extracted by different invariance modules are distinguished by different colors. For example, the first pattern, num_j, represents an intra-invariance pattern extracted from the first 2 rows in concept matrix J with respect to the attribute number. Now, you may have a question. How can we make use of all these patterns to solve RPMs? Let's move to step 3 to find the answer. For answer selection task, we should insert every answer option in the missing panel, and then compute the number of patterns that are common to all 3 rows. The correct answer is the answer option that maximizes the number of common patterns. The table below shows the results for our running example. Hence, the third answer option is selected as the correct answer. For answer generation task, we should generate answers without any given answer options. Since every pattern is extracted by one of the invariance modules, intuitively, we just need to apply the inverse invariance modules to the last row and infer the corresponding attribute values for the missing panel. For the algorithms of the inverse invariance modules, please refer to the appendix of our paper. Below are the computational results of the concept of the inferred answer for our running example. From the 6 intra-invariance patterns with respect to number and position, we can infer that there should also be 2 entities in J33, with one entity inside and the other entity outside. From the next 4 intra-invariance patterns, we can compute the type, color, and size values for the outer entity, as well as the size value for the inner entity. From the following 2 inter-invariance patterns with respect to color, we can infer that there is at least one white entity in J33, and the inner entity must be black. From the last compositional invariance pattern, we can compute that the type value of the inner entity is pentagon. As a result, the concept for the inferred answer is given below, which is consistent with the given answer. Thank you for watching.